calculate the number of molecules in 30 nanograms of ammonia, also known as azane NH3. In this case, we will solve the problem using two techniques, the chemical conversion factor and algebraic theorems. We will start with the chemical conversion factor. The first step is to write the given data in the chemical conversion factor format, where each term consists of a value, a unit of measure, and a substance identity. In this case, we have 30 nanograms of ammonia. Then, we multiply by the first conversion factor, which involves placing nanograms of ammonia in the denominator and grams of ammonia in the numerator. Since the gram is a larger unit, we establish that 1 gram equals 10 to the power of 9 nanograms. In the second conversion factor, we place grams of ammonia in the denominator and moles of ammonia in the numerator. Here, we assign the theoretical unit to the mole and determine how many grams are in a mole. The answer to this question is the molar mass. To calculate the molar mass of ammonia, we add the molar mass of nitrogen, 14.01 grams per mole, with 3 times the molar mass of hydrogen, 3 times 1.01 grams per mole. The result is 17.04 grams per mole. In the next conversion factor, we place moles in the denominator and molecules of ammonia in the numerator. Again, the mole carries the theoretical unit, and the number of molecules in a mole of any substance is always Avogadro's number, which is 6.022 times 10 to the power of 23. In the dimensional analysis, we cancel out the units and the ones that multiply and divide. If any unit has significant figures, they must be taken into account. We extract the significant values to insert them into the calculator, and the result is 1.1 times 10 to the power of 15 molecules of ammonia. To apply the theorem, we select the corresponding one from our formula sheet, which indicates that the number of molecules, represented by italic N subscript J, is equivalent to the product of Avogadro's constant times the given mass, divided by the molar mass. We simply follow the equation. In the formula, we substitute J with the identity of the substance, which in this case is the molecular formula of the substance. Then, we substitute Avogadro's number with 6.022 times 10 to the 23 in units of 1 per mole, the mass with 30 nanograms, and the molar mass with 17.04 grams per mole. Additionally, we substitute nano with its definition, which is 10 to the negative 9, derived from the decimal prefixes table. Notice that in this method, the identity is contained in the dependent variable and does not need to be placed in the operational terms. When performing the dimensional analysis, the units cancel out, which makes sense, as in algebraic form the number of entities is a dimensionless parameter. This differentiates it from the conversion factor method. By eliminating the ones, we find that the significant terms are the same as those generated by the conversion factor, so the value is the same, 1.1 times 10 to the 15. In this case, it is understood by the italic capital N of the theorem that we are talking about entities of ammonia. Since ammonia is a molecular substance, we are implicitly talking about molecules, without the need to express it with units and identities as done in the conversion factors. Since the only actual data is 30 nanograms, we count only 2 significant figures, and the answer is given in 2 significant figures. Well, that's all for now. If you liked the presentation, don't forget to subscribe, like, and share. That keeps this channel alive. See you next time.